Well, hello. My name is Ian Document, and I hope you're ready to learn some math today because today we will be learning how to solve a differential equation as a separable differential equation. So without further ado, let's get started. So first things first, let's take a look at our givens. To start, we're given the equation y prime is equal to r minus ky, where y naught is equal to 180 milligrams per deciliter, r is equal to 32 milligrams per deciliter hour, and k is equal to 0.27 per hour. If you're curious where these numbers are coming from, you can read the accompanying paper to this video where we explain the derivation of all three of these units, or all three of these numbers. But to keep it brief, we are modeling glucose levels in the blood of diabetic patients using this differential equation here. So without further ado, let's get started. So first things first, we're going to take our given and re-express y prime as the fraction dy over dt. Now this isn't actually a fraction, but it is convenient to think of it as one for the sake of a separable differential equation, and it actually works out in this case. So we can express that dy over dt is equal to r minus ky. From there we can just express it again for clarity without the y prime, and we just have dy over dt is equal to r minus ky. From there, we're going to want to cross multiply so that all of our terms that are dependent on y are on the left side of the equation, and all of our terms that are dependent on t are on the right side of the equation, where this is where the separation comes in separable equation. So as you can see, we have dy over r minus ky is equal to dt. And since both sides of this equation are equal, that means that their integrals will be equal. So we now have that the integral of dy over r minus ky is equal to the integral of dt. From there, we just carry out this integration, pretty straightforward stuff, and we have negative 1 over k times the natural logarithm of r minus ky is equal to t plus c. And keep in mind with this constant, technically speaking, both of these integrations produced a constant, but we just implicitly add them together since a constant plus a constant is still a constant, and it just simplifies cleaner later on to have all your constants together. So pressing on, we then take some simplifying steps. We multiply both sides of the equation by negative k to eliminate that negative 1 over k. And so now we have the natural logarithm of r minus ky is equal to negative kt plus c. And that c absorbs that negative k there because it's a constant and it can absorb the multiplication operation. From there, we then exponentiate both sides, and we have r minus ky is equal to e to the negative kt plus c. Finally, we're going to subtract this r from both sides, and we're going to divide both sides by negative k so that we can isolate y and have it as a function of time. So as you can see here, we have the equation y is equal to c times e to the negative kt minus r all over negative k. So this c is going to absorb this negative k division, and this r and this k, their negatives are going to cancel out, and we're going to have the general form of the solution. Y of t is equal to r over k plus c times e to the negative kt. From there, it's pretty straightforward. We can now solve the initial value problem. So we first just take our inputs. So y naught is equal to 180, which is equal to 32 over 0.27. And these numbers are coming from the given up top. And then we add that to c plus c times e to the 0. And e to the 0 is just 1. So some pretty simple algebra from here. We just move this fraction to the other side, sum them together, and we have c is equal to 61.48, which is about 61. So we're going to approximate our constant here since our initial data is approximated, and so we want to keep a consistent amount of significant figures. So 2 or 3 significant figures would be appropriate in this case since our data only has 2. And there you have it. The equation is solved. We now have our solution curve, which is y of t is equal to 61.5 e to the negative 0.27 t plus 118.5. And as you can see, I decided to add one more degree of precision to our constant here, just so it looks a little closer to the hypothetical no error function. But there you go. There is a separable differential equation solved. I hope you learned something today and that you have a wonderful rest of your day.